start the CAN seminar. So good afternoon, everyone. Thank you again to join our weekly CAN seminar series. And today we are honored to have Professor John Haddock. So Professor Haddock is registered professional engineer and a professor of civil engineering at Purdue University. Here, he also served as the director of the Indiana Local Technical Assistant Program. During his career, he has worked in research, equipment and test method development, and criteria and specification writing. He has been responsible for asphalt mixtures, design production, forensic pavement investigation, and pavement design and analysis. Professor Haddock earned his bachelor's and master's degree from Purdue University and his doctorate from Auburn University. And before we proceed, I would like to invite Professor Alkadi again to complement this introduction.
Yeah, John, welcome to University of Illinois. We really appreciate you joining us. I've known John for at least 25 years and always enjoy his work and his presentation. And we're very, very pleased to have you with us today. So John, the floor is yours.
Well, thanks.
Sorry, Professor Haddock, just a little bit housekeeping things. Just a reminder, Professor Haddock will have 30 minutes of presentation and continue with 20 minutes of Q&A. And if you have questions, you can go to the participant buttons. There is a raise hand option there. You could raise your hand and ask the question directly during the Q&A. Or you can type the question in the chat box and I will ask them for you in the Q&A. Professor Haddock, please.
Okay, thanks. So the first thing I need is whoever has control of the Zoom meeting to let me share my slides.
Sure.
You should be able to do that now.
Yep.
Oh, yep, there it is. Thank you. There we go. Let me just do a little housekeeping and take some of this stuff off my screen. Okay, there we go. Well, thanks for the invitation. I'm sorry that we can't all be together. It's not a terribly long drive for me from home here to the University of Illinois. It takes me past the Beef House, if any of you are familiar with the Beef House, for me to get from here to there from University of Illinois. Of course, we always have to stop there. So my understanding is there's some interest in from the students at the University of Illinois maybe to understand a little more about the Aspire Center. So this NSF Engineering Research Center that we are part of. And so what we're going to talk today about today is the Aspire Research Center. And you can see I've entitled this talk really a pavement perspective with dynamic wireless charging for heavy trucks. So the ASPIRE is an acronym. You can see it stands for Advancing Sustainability Through Powered Infrastructure for Roadway Electrification. And whenever we say that, we get a lot of funny looks from people. They always think, what, you're going to try and electrify pavements? Well, we are. We're not really electrifying the pavements. We're putting something in the pavements that's electrified. So just as a kind of an overview, I'll try and give you a little overview of the Aspire Center and then talk towards the end more specifically about the pavements themselves, because that's what I do. I'm in pavements and pavements materials. So the Aspire Center has, you can see here, they're basically, there were 4 original members that you see here. There's Utah State, which is where the center is actually located, the headquarters, the University of Colorado, University of Texas, El Paso, and of course, Purdue University. We're the 4 major universities that are part of the Aspire Center. We do have an international partner working with us. You can see that's the University of Auckland in Auckland, New Zealand. They also are part of the center. And then you can see as you look around, there are some other universities that are affiliate type members like Colorado State, University of Colorado, Colorado Springs, Cornell University, Virginia Tech, and then there are some of the national labs that are also partnered up with us in the Aspire Center. So we're really spread out across the United States, as you can see, at least across the contiguous 48 United States. And of course, internationally, you see if you look over in the corner, we do have some partners that are working with us in both Israel and Sweden, and of course, New Zealand as well. So there's an international bent to the center also. We also have several partners that come from, when you look at this list, I know it's really a busy slide, there's a lot of them. You can see we do have some state DOTs that are involved with us. You can see again the national labs, the energy companies. Obviously, this is a big deal for them. If you're going to use electricity to do this, you're going to need to have the people producing and moving electricity around working with you. And you can see basically the OEMs, the original equipment manufacturers as well, that are involved. So there's quite a large contingent that have partnered up with the center also. Just as a kind of a, this mission kind of a thing, you can see that really what the Aspire Center is trying to achieve. You can see that sustainable and equitable future of transportation there. And it's really about the widespread electrification across vehicle classes and adoption groups. You may be aware that, for example, General Motors has announced that I think it's by 2030 or 2035, I can't remember, that they're only going to sell electric vehicles. I think that's probably that trend is going to increase amongst the all auto manufacturers. And so that's one thing that we're looking at. The other thing, of course, is heavy trucks, and we'll talk more about that later. The impetus really for the Aspire Center, you can see that in the background of that slide, that is Salt Lake City, Utah, if you've never been there. And one of the impetuses for this is, if you've ever been to Utah, you realize that almost the entire population of the state of Utah lives in a very fairly short, narrow valley, or two valleys that go up and down the Wasatch Front. And they have real problems with, in certain times of the winter, they'll get inversions, and they have real problems with smog. Because of their I-15 basically is the major corridor that goes up and down the valley. And that's what really got Utah State thinking about this originally. And so the whole vision here is this widespread electrification to try and improve human health, human prosperity, and equity and access, because we're really trying to electrify the vehicle fleet in the United States. So just to kind of give you an overview of it, there's really several things going on here. There's low and medium term parking. You can see here, the idea that we're working with is actually to embed the charging systems in the pavement, so that when you, for example, in this scenario, you park your car and it automatically begins charging as soon as you park there. Now, of course, long and medium term parking, charging for electric vehicles is already out there. It exists. So for example, if you go to the Indianapolis airport, where you might park for a week at a time or something while you're traveling, if you have an electric vehicle, you can actually plug in. And that's true of a lot of different types of places you can go and park your car. But today you usually would plug in. What we're talking about is actually embedding the charging systems in the pavement. And it's a wireless power transfer. So when you get over the system, your vehicle begins to charge the battery automatically. There's also short-term parking and low speed. There are systems like this that are deployed as well today, most of them in buses, for example, where the buses run on battery and they are charged either at points where they stop, or they can be charged with a wireless power transfer by putting that in the pavement as well. And of course, the real kind of maybe the hardest thing to achieve is the high speed charging. And so the way this would work is again, as you drive down the highway, your battery gets charged as you move along. And that system is actually embedded in the pavement, and it wirelessly charges your battery. So there are some pilot projects out there that demonstrate that this can be done. Not really at the highway speeds. We intend to work at highway speeds, in the 60 to 70 mile per hour range where you do this. So for those of you who are old enough to have played with race car tracks when you were little kids growing up, this is kind of the same thing. The car is going to actually draw power from the road as it moves down the road. And that's quite an undertaking that we're working on. So the whole point being is that one of the problems with electric vehicles is range anxiety. If you have an electric car, you probably know you're limited to somewhere around 250 to 300 miles before you have to charge that battery. And when you do actually go to charge it, it takes a while to charge it. And so this is a a method that we are trying to work on here to try and avoid the range anxiety so that you can keep your battery charged as you move around. Just some background you see in this slide, you know, where are the roads, for example. You can see that a very small percentage of the roads you see here are actually interstates, but they carry a significant amount of traffic. And if we went into heavy truck traffic, that would be an even bigger deal. If we went by easels, for example, rather than miles driven. But you can see here, you know, most of our roads are rural. However, the largest share of traffic in miles driven is carried by those urban roads. And then you can see over here on the left side that basically here's basically the lighter duty trucks you can see that make up the fleet. These are the heavy trucks. Okay, these are the trucks that move the vast majority of freight by truck in the U.S. And we are working to try and electrify those fleet as well. We do have partnerships with various companies that build trucks and are working with them also. And then you can see some, you know, other things like the air and the rail and things in there. So we're really looking at basically taking, you know, this largest share of the pie and trying to electrify that, and then be able to charge those electric vehicles as they move about on their daily errands or whatever they're about. You've most likely seen this particular slide for at least the one on the right. It shows you basically the transportation network really by how heavy the traffic is. And you can see those heavy red routes. Those are, for the most part, heavy truck routes for shipping freight around the U.S. So, for example, you can see there's the Chicago area right there. In fact, that red dot's so big you can hardly see my red dot pointer there on it. And then you can see there's Indianapolis, which, if you're familiar at all with the state of Indiana, we're called the Crossroads of America because all those interstates cross right in Indianapolis. Most people think it's because, well, when people come to the crossroads, they go through it as fast as they can, so they're not here in Indiana any longer. It's really because of all those highways. And so you can see, the thing is, if you begin to look at the power network in the U.S., where the power generating capability is distributed, you can see that it matches fairly well with where these heavy routes are. And so that's good because it's going to take a lot of power to try and electrify at least all these truck routes. Now, we don't really foresee in the future every road in America being electrified so that you can do this with, but there would be certain truck routes that would be electrified like this so that you could use electric vehicles to move freight around more easily. And this is an overview when you look at this slide that kind of gives you an idea of you know, the whole vision, everything working together, where it's, if you start on the right, it's anything from electrified trains, which obviously are easily implemented. Those exist already in many places in the world, through wireless charging for buses, for example, wireless charging for personal vehicles, you know, cars and light trucks, all the way up to running heavy trucks, heavy freight trucks. So one of the problems when you begin to try and electrify heavy trucks is that if you have to have all the batteries that you need to run that, it really decreases the amount of usable weight that can be used to move the freight because the batteries become so heavy on the truck. So part of the vision of Aspire is that because these trucks can charge their batteries as they move along the roadway, they wouldn't need as many batteries. And so it would cut down on the weight of the batteries as well. And of course, the vision is to try and integrate, you know, either wind or solar energy, renewable type energy into this whole scenario. So this kind of paints you a vision for the future of how this would all work and how this would all tie together. Now, as you look at that, you're probably thinking this is a huge, massive undertaking. And you're right, it is, because not only do we have to worry about things like I worry about is how do we get these charging systems in the pavement so that they don't damage our pavements at all, the durability of our pavements, but you have to work your way all the way up to the grid itself. How is the grid supposed to do this? If you know anything about the electrical grid in the U.S., you know that it's fairly old, and it's had some problems and continues to have some problems and really needs to have some work done to it. And so that's part of it as well. And so we're really going through everything from the electrical grid all the way down to embedding these systems in pavements. All right, so if we talk a little bit about the transportation, you can see here, obviously on the left is just looking at the transportation life cycle, for example, of a roadway, where we do the planning, the design, the construction, the maintenance, reconstruction, and it goes around and around. And then what I have here, what you can see is the report card. This is an older report card. The 2020 report card just came out in the last couple of weeks. But we didn't get a lot of improvement. And the big three that you look at that we're talking about here is if you look at our roads, you know, ASCE rates our roads somewhere around a D, and our energy system somewhere around a D+, and transit somewhere around a D-, which, by the way, for those of us that work and go to school at universities, we know typically tend to be passing grades, but nobody wants to drive across the bridge that was designed by somebody that got a D- in structures class. So there's really, we're really at that point where there's this huge opportunity, because the energy grid needs to be rebuilt, because the road system needs to be basically you know, rebuilt, much of it. We're kind of at a point in the US where we could really begin to integrate new systems into our transportation systems, so that we end up with something that it not only functions well, but it's sustainable and it's equitable for everyone. If you look at impact across these different things, you know, so anything from the grid, so the impact it would have on the grid by upgrading the grid, and then, you know, through vehicles, through users, and through the environment, all the things that could be done. What we'll focus a lot on today is basically this vehicle, and really the idea of trying to get these systems in the pavements so that they work correctly. And so the Aspire Center is really here to try and determine, you know, how this can all be done. It's a huge undertaking. We have a lot of different people from a lot of different places working to do this. I just kind of give you an idea here of the different areas that we're working in. And so there's power research as part of the Aspire Center going on. This group of people, they are the electrical engineers of the bunch, and they are working on, you know, trying to figure out how you get all that power, the power that you need, and get it where it needs to be, and how you actually power these systems up. You can see here, this is a mock-up of what the system might look like inside a pavement. Here it looks like, you know, something, this could be one of the powerless charging systems that goes into the road. You can actually see there's actually some real components that they've been working on there. How do we get all that in the road, though, is the real question. And the power group is working on how you basically take that power, get it into the road so that it works correctly, and so that no one gets hurt. There's actually an adoption part to the research. The adoption team, what they're working on is, how do we get acceptance from society? I mentioned earlier, you know, when we mentioned that we want to electrify pavements, people have this shocked look on their face, no pun intended, because they're thinking, well, how can you make a pavement electric? What happens when I get out and stand on that? Well, it's safe. It's not a problem. It's not like the pavement itself is electrified. It's just parts that are in there. And so this particular group of people that you see here, they're working on the user acceptance, the public policy, the economics of it, those types of things. And you can see here, they're doing all these different types of things in order to get us from the lab out into pilot projects on the road. There's also a data research team. And one of the things a lot of people don't think about when you think about all this is the amount of data that has to be moved to do this. So for example, if you have this kind of a charging system in the road, it's not turned on unless there is a vehicle that is asking for it to be turned on. So as you drive your car along the lane that has the electric components embedded in it, as you approach that, your car needs to be able to talk to the road, tell it that I'm coming, here I am, I'm going to be there in 5 seconds. It needs to turn that system on so it charges only your battery, and then when you move off of it, it has to turn that system off. So there's quite a bit of data that has to be moved around. And all of that data has to be protected from people that would want to hack into it, because you can well imagine if someone hacked into such a system, they could cause a lot of grief. And so this team is working on that part of it. You can see all that the big data type of stuff that has to be done to get this to work correctly. And finally, the last real research thrust that we have as part of it is the transportation research thrust, which is broken into two areas. I would call that hard transportation and soft transportation, but that's just me. Hard transportation meaning the infrastructure. That's what I work on. I'm working on things about, you know, how do we get these charging systems into the roads? How do they interact with the materials? How do they interact with the pavements that, you know, once we get them built? And then the soft transportation, what you see here is transportation systems. Then they're worried about, you know, travel demand. How's all this going to work, you know, when people start traveling up and down the road and those sorts of things. So what we're trying to do is an extremely large optimization problem. You can see here we just have a couple of mock-ups of the charging systems themselves. So basically what happens, you can see it over here. And for those of you who may know more about electrical engineering than I do, please excuse me. But basically the way this works is that there's a roadside where the power comes in, and then as your car moves over, it's wirely transferred over to the vehicle side. And that typically, or at least we perceive that being done basically using a magnetic field. So what happens is you drive over the embedded system in the pavement, it creates a magnetic field. That magnetic field is shaped so that it pushes the field up towards the vehicle. And then there's a receiver on the car. And then that's how the electricity is actually is transferred from the road or from the system in the road to the car through a magnetic field. So it's not like you know, have something dragging on the pavement to try and pick that electricity up. And so trying to optimize this is a huge problem. And one of those things is how do we integrate all these components into the system? And in my case, how do we get those into a pavement? And how do we get them to hold up under the traffic and the environment that they're going to see? And conversely, how do we get the pavement not to lose durability because these systems exist in it? Just a little more about this. So you can see here from the infrastructure side, what I refer to as hard transportation. What we're really trying to do is, from a pavement perspective, we want to make sure that this is affordable when we put these things in a pavement, that it not cost so much money that it becomes cost prohibitive. We want to still make it constructible. We want to make sure the pavements remain durable, and we have to be able to maintain those pavements. So these are really the things that we're looking at. Whereas you can see that the transportation systems folks are really looking at reliable, safe, getting the optimal charging ports. You know, where do those charging stations need to be in the road? And of course, do we have adequate charging lanes, right? If everybody's driving electric vehicles, do all the lanes need to be have these, or can we just have one or two lanes that actually have these systems in them? This is a little background about the facilities that exist where we're doing the work for the Aspire Center. You can see there's the Aspire headquarters. Aspire is headquartered at Utah State University, which is in Logan, Utah. If you've never been there, it is a beautiful, beautiful place surrounded by the mountains. But there is a reason that it's known as the ice box of Utah. It gets extremely cold there in the wintertime. The Utah State also has this facility that you see here. It's called their EVR facility. It's basically a quarter-mile track with some attendant buildings, and you can see they have some solar cells or some solar panels now where they're generating electricity from the sun. And basically what this does is a low-speed facility where we can actually put trials into the pavement, and they have a small bus and an electric car, and they can actually traffic, and we can gather some data doing that. Because it's only a quarter of a mile track, it's not a high-speed facility. You cannot reach highway speeds on it because the corners aren't banked or anything like that. There is the EVR along with it. You can see in the building right here, there's a research facility there. Utah State does have their structures lab where they've done some testing on some of the components. The Granger Power Magnetics lab here at Purdue University is part of it. And of course, our asphalt research lab, we're involved in it as well. We have an accelerated pavement testing facility here at Purdue that you can see there. That's part of it. By the way, for those of you who've seen the accelerated pavement facility at the University of Illinois, I think it was really, I think they looked at the design we had here and made it something that was even better. They have a much better facility there at the University of Illinois than we do. Ours is fairly short. Yours is fairly long. The materials testing lab, you can see at University of Texas, El Paso. There's this simulation lab at the University of Colorado Boulder, which is really a lot of fun, where they can simulate whole cities, and you can simulate traffic moving around. It's really interesting when they do this. The power electronics lab at Colorado, and then Auckland also has not only their power transfer lab, but they are in the throes of also building an accelerated pavement test facility at the University of Auckland as well. So that's just a little background into the different labs and the equipment that we have that are available that are working on the problem. Now, having said that, giving you some kind of a background on Aspire, let's talk a little bit about pavement challenges. So how do we get these systems into pavements? That's what I'm most interested in. I've been involved with Aspire and the forerunner of Aspire for several years now. And when I first got involved with them, it was mostly electrical engineers that were involved. And I started asking a lot of questions about how's this going to work in pavements. And today, those are the problems that we're trying to solve pavement-wise. So we really have to worry about, you can see I have two types of pavements here, right? Rigid on the left, flexible on the right. Composite pavements are also a concern. We are doing some work with composite pavements as well. So, for example, one of the owners of the tollway came to us and said, you know, we would really like to have a system that has concrete that has asphalt over the top of it. And can we put these systems in those as well? And so really there are three, rigid, flexible, and composite that we have to sort of worry about. So just from a loading standpoint, how are these systems going to hold up to traffic? If you think about putting these charging systems into pavement, you're basically putting an inclusion into your pavement. What's that going to do to your pavement? One of the early things that I said was, look, let's don't put inclusions in the pavements that have sharp edges, right? So let's make the systems round or oval as opposed to square or rectangular, so that we don't cause more stress. And so, so loading, when we have these heavy loads on the systems, how's that going to work? I can say to date, the testing that we have done in the lab, in the structures lab, and with finite element analysis seems to indicate that these systems will be able to withstand traffic without any problem, and they should not be a problem when they're included in the pavement. How are they going to handle the environment? That is an excellent question, and we've got quite a bit of work going on in that as well, especially when it comes to thermal management, because if you think about it, you're basically taking electricity, you're driving it through an inclusion in the pavement, using that electricity to set up a magnetic field that's going to cause heat, which means that you have to have some kind of a thermal management system. Obviously, if you heat the pavement up with a system like this, it's not good, particularly for an asphalt type pavement. You don't want that to be hot. It could cause rutting. We're not really sure, for example, what would happen if even within a rigid pavement, if this much heat was generated in a concrete pavement and not dissipated properly. So there's quite a bit of work going on for thermal management, for thermal loading stresses on pavements, and how we dump that thermal energy that comes from these systems. Pavement design, are there any challenges that are going to come about from a pavement design standpoint? You can see I just have, there are a lot of different ways that we can design pavements, different methods. But many of the states in the United States now are using Pavement ME, which is the mechanistic empirical pavement design method. And are we going to have to change? Are these systems going to cause us to have to change how we design the pavements? that is a question that has not been addressed or answered at this point. And then there are materials challenges. If you think of it, you know, if you have I mentioned this earlier, if you have either an asphalt or a concrete pavement, how is the heat that's generated from these systems, how's it going to affect those pavements? Is it going to do some damage to them? Is it going to shorten the durability of a pavement because we've now put these systems in it? If you're looking again at rigid pavements, you know, we're putting dowel bars in it. If we're putting reinforcing steel in rigid pavements, now we actually have included in the pavement these systems that electricity is being run into. How's that going to affect dowel bars, for example, or reinforcing steel in pavements that have reinforcing steel in them? Those are questions you have to ask as well. Obviously, we don't want to, you know, have a case where we are doing anything to decrease the durability. One of the early things that we brought up was just from an aggregate standpoint. So there are places, for example, in the US, the Midwest here being one of them, Indiana and Illinois, both use slag, for example, in their pavements. And slag's a byproduct of, you know, the steel industry. How are these systems going to affect those materials? You know, how are these systems going to affect long-term, for example, the durability of, you know, the binder grade, for example, that we put in an asphalt, or how are they going to affect the cement that we put into a concrete pavement? So these are questions that we are now looking into, and we'll continue to look into the future of the center. There are also construction challenges. How do we get these systems into the pavement and get them in a cost-effective manner? And so I have, you know, a couple of photos. Well, obviously, you know, here's a concrete paving machine. Here's an asphalt paving machine. We have a pretty good handle on how we build pavements today. But when we begin to put these systems in the pavement, this is an actual system being put into a pavement. It's actually just a test facility. And so you can see in this case, what they've done is they've come in and they actually have milled out this narrow this narrow spot in the pavement where they drop their system in, and then they'll come back in and they'll pave over that. They'll just pave over that. That may or may not be a really good approach for high speed traffic. We're not really sure yet, especially when you talk about heavy trucks. For this to work, for example, with a, you know, for your passenger car, you know, it doesn't take all that much power. But in order to do this with heavy trucks, you're talking about something in the neighborhood of 200 kilowatts. So it's a real high power level that has to be done in order to get it to work. And so these types of installations have been made on very short pilot type projects. And you can see what they're working on here is actually a research spot where they actually just have a trench that they have put into their pavement, and they can cover that trench up and uncover it as they go, so they can actually work in it. That's probably not a viable method as well long term. So actually trying to build these is something that we're working on as well. One of the early thoughts is well, we could put these systems prefab into concrete panels, which can then just be simply dropped into place and connected up in the field. So they basically would snap together like a large Lego set, and all the electronic connections are made, and then you're able to go on. And then if anything fails, if you have a failure in a panel, you can simply take that panel out, snap in a new panel. Whether or not that comes to fruition, I'm not sure, but it's certainly one method that has been discussed and thought about. Again, from a maintenance standpoint, you realize we have to do maintenance on pavements. And a lot of times, at least with flexible pavements, that maintenance involves something that looks like this. And so one of the early questions I ask is, how do you suppose those milling teeth, you know, what are they going to do to your electronic system that's built in the pavement? One of the things that in doing these the dynamic wireless power transfer is that you have to try and keep the gap closed between the system that's in the pavement and the receiver that's on the bottom of the vehicle. The closer those two are together, the easier it is to transfer that power. And so the electrical engineers tell us that they would like to try and keep these systems within about 2 inches of the surface of the pavement. And that way you could put, the receiver on the bottom of a vehicle, and you could set it so that they would like to try and maintain something on the order of around a 10-inch gap. And so if we're going to bury these so that they're only 2 inches down, that's going to affect some of the maintenance things that we do. And it's pretty common to maybe go out on an asphalt on a flexible pavement and mill, maybe 1 inch to 1.5 inches of the surface and replace it. But you've got to make sure you never get down into those electric systems when you do that. And so maintenance becomes a problem. Also, if you're have to do some concrete maintenance, what's that going to look like with these systems as well? These are all unknowns that we're not sure about, but are things that we're working on and trying to define as part of the center and the work that the center is doing. So as a research approach, this is basically we're going from testing in the lab to full-scale accelerated loading tests. Then we'll go to some small pilot tests, and then we'll go to really full-scale testing. And so you can see basically here, if you look at this picture, this is actually one of the charging systems being embedded in concrete. And you're looking at that and you're saying, by gosh, they put that in a square, didn't they? Well, the coil's round, but they put it in a square piece of concrete. So there's going to have, stress points on it. But anyway, we're doing lab testing. Much of the concrete testing that's being done is being done at Utah State University in these systems. We'll take what we get from the lab, we will then use that to inform what we do in full-scale accelerated testing. So the intent right now is to put these systems into our full-scale accelerator here at Purdue. We can actually bury those. You can see the pavement here. Our pit is only 20 feet by 20 feet by 6 feet deep. So it limits to what we can put in the system, but we can put the system full scale in here, use regular construction methods to put it in. We can not only traffic it, this is actually half a semi tractor trailer there. We can put, typically we put 9,000 pounds on it since it's half an axle. We can traffic it. We can also then measure the thermal properties that are going to come from the system, of the full scale system as well. The idea then would be for us to build a small pilot project. We in Indiana are trying to identify now where we might put one of those. Oddly enough, one of the locations that is in the running is State Road 63 down near I-74. So if you're familiar with that area, it's just inside the Indiana-Illinois border on the Indiana side. It is very near the Beef House, for those of you who know where the Beef House is. But anyway, that may be a spot where we're actually able to use a small pilot project. When I say a small pilot project, we'll use full-scale construction to do it, but we're only planning on building somewhere in the neighborhood of about 1/4 mile, 400 meters of a small pilot project, just to get a feel for how it's going to work and to give us a test bed out in the environment. And eventually, the thought is within about 5 years, we'd like to have a full-scale deployment be done, where we actually put this in a location where it can be used by heavy trucks quite often. For us in Indiana, that's probably somewhere on the I-70 corridor. If you're familiar with I-70 corridor, from Indianapolis to Columbus, it is a major, it's a major freight route. And so this is what the traffic on I-70 looks like pretty much all the time. It's a lot of heavy trucks. And that would give us a place then to put this in where we could then use heavy trucks to traffic it and get even more information about it. So having said that, I know it was a really quick overview of the center itself and some of the concerns that we have from a pavement standpoint, but I'll stop there and try and answer any questions anybody may have. I'm sure that you have questions that about things that I did not address in the talk. So any questions?
Thank you so much, Professor. It's a very great talk. There's a lot of topics that's covered, and it's very interesting to know how this pavement for electric charging is going to be looks like in the futures. So I think we have several question in the chat box. It's from Amir Malakuti. He asks, does wireless power transfer system create noises for communication device, for example, phones?
You know, that's a good question. The idea is that it shouldn't, because the wireless power transfer, the power is magnetically shaped so that it only is shaped into that receiver on the underside of the car. And I think the question has to do with the fact, if you're driving down the road, you're not going to get cell phone reception, or is it going to do something odd to your cell phone as you drive over it? And the answer is no, it shouldn't, if it's done correctly. At least that's my understanding from electrical engineers.
Sure, great. And I believe there's another question from Tom Burnham. It's asking who's funding this. I think it's more on funding the project.
Yeah, I didn't put a funding slide in. So Aspire is an NSF, Engineering Research Center. So some of the money is coming from NSF over the total life of the center. That is projected to be about $50 million. But we also get considerable funding from a lot of our partners as well. So over 10 years, the center is expected to have about somewhere in the neighborhood of about $250 million that goes through the center in about 10 years. But that's not all from NSF. Part of it is there's some obviously some sharing of resources from the universities that are involved, but there's also a lot coming in from, for example, from state DOTs. There's money coming in for from the manufacturers, car manufacturers, some of the other people that work in this space as well. So it's all the partnerships are part of it also.
Sure, great. And okay. So if everyone, yep, we have Professor Kuntu here. Professor, you can unmute yourself.
Sure. Thank you, Professor Haddock, for the very interesting presentation on wireless power transfer charging. This is a technology, you're in the forefront of this technology, right? I wonder about funding, but from the perspective of who would you anticipate funding this effort in the long run for placing this infrastructure in the pavements? And also, how would, in that system, pricing would be facilitated, given that we are talking about federal interstates, for example, versus private entities that would be willing, I guess, to go after this type of private public agreements, right? So this creates a very interesting type of partnership there. Do you envision something like that?
Yeah, in fact, the P3 is kind of part of what, one of the research thrusts is doing. So, I mean, you ask a good question, are the state DOTs going to want to fund this? Well, they may want to fund some routes, but in order to do this, you have to have a partnership with the company that provides the energy, correct? Somebody has to provide all that energy, and so they have to be involved, and that means somebody has to pay for the energy. So I think, at least the thinking I heard, and please, this is not my area, not what I do, but in the meetings that I've been in, what I've heard is the vision really is that part of the data transfer would be, as you drive down the road over the system would know that you're drawing energy from it, and it's going to charge you for that, right? Mm-hmm. So you would pay to do that, to charge your battery basically as you move along. Now that's one scenario. There could be a scenario, for example, if it were a toll road, they may simply include that pricing in their tolls as a way to do it, as another example. Again, I don't think anybody envisions all the roads in the U.S. having this sort of a system, but there would be roads in strategic places that have this, I think.
Sure, thank you.
Hi, John. This is Errol Tutum. Excellent presentation, John. I have a question. You showed some, I guess, parking lot charging locations already. I was curious whether there are constructed such parking lot charging positions or pavements already been tried and built?
So yeah, so there are places where they've done, some, testing. For example, a company that does this may actually have put that in some of their parking spaces so that there are people that can use it. Now, obviously, one of the problems you have when you do this and you park over it is you got to be aligned, right? The receiver on the bottom of the car has to be properly aligned, and there's technology that has to be able to do that. If you have an electric car, you can actually buy a charger like this that's not necessarily embedded in your pavement, but you can sit on your garage floor, for example, and when you pull in over it, you can charge the car using that sort of a thing as well. So they've not been embedded in pavements, Errol, widely, but there are some places out there that have done it just as a kind of a proof of concept sort of a thing.
Great, thanks.
I will say this as well. There are a few bus companies in the U.S. that have put this system in. One of our company partners is a company called Wave. They put these type of systems in pavements, and so they're embedded in the pavement. And as the bus comes up to the bus stop and stops, it actually puts itself over one of these systems and starts to draw power from it while it's making a stop.
Oh, excellent. Great. Thanks.
Hi, Dennis. I have a question. This is Kamal from Carleton University in Ottawa, Canada. It's a great presentation, Professor Haddock. But from the practical point of view, I feel like it still will take lots of time to make it happen in the real world condition after even if this research gives positive result to apply. What about to install those sensor, Wi-Fi sensor or electric sensor on the side of the road, on the sidewalk or on the embankment rather than in the main structure? Is that discussion happened or that is also not feasible?
So there are some pilots there are pilot projects in the world where they actually do have the system built at the side of the road, and it can draw power even from the side of the road. But those are obviously, you've got something out there now that a car can run into, right? There's become some safety issues with that. Those systems were built more as a proof of concept that you could draw power this way, as opposed to actually a long-term solution. But some of the sensors and things like that certainly could be on the side of the road. And certainly, there'll have to be electrical types of things that are at the side of the road also, right? So power inverters and those sorts of things that have to come in order for the grid to interact with these systems, all that would have to be put at the side of the road somewhere. Now, whether it's buried in the ground along the side of the road or it's standing along the side of the road, I'm not sure which it will be.
So what is the main issue then? I mean, if you put those things in the pavement structure, main structure, so it's getting the low deflection, those kind of thing. It does not help to generate the electricity. You are just bringing the electricity from the electric grid or windmill or the other system, solar energy. So why it is not feasible to put in the side rather than in the pavement structure?
So are we talking about the charging system itself?
Yes.
So if you put the charging system at the side of the road, why not do that? Then the question becomes, how do you transfer the power to the vehicles that moves past it?
Oh, so it's a distance thing, as you mentioned in the talk. It needs to be in 2 inch. That is the problem.
The electrical engineers keep telling me they don't want any more. They don't want a bigger gap than 10 inches.
Okay. That makes sense.
Yes, you have to be able to transfer that power, right? So people like me, when I was a kid, we had little racetrack sets, and the cars on the underside of the car, it had 2 little metal rails on there, and they actually interacted with the track that had metal leads embedded in the track, and that's how they drew power. So it's sort of like that, only in this case, there's nothing rubbing on the pavement.
Oh.
By the way, you bring up a good point. I think the holy grail would be if you could use the pavement to generate the power, right? Think of all the square feet of pavement that is out there, and what if that all collected solar power from the sun, and then that was used to charge? I think that's kind of the holy grail, but The Aspire Center is not working on that at all.
Okay. Okay. No, thank you. It explains actually. Okay. Excellent.
Okay, great. I think we have another question from Angeli.
Thank you, Denisa. Thank you, Professor Haddock. Really interesting talk. It just came to mind with respect to the maintenance procedures. I was just curious, what is the lifetime of such embedded systems? Because then it would be also nice to tie that, right, if you were to do a major rehabilitation. So I was curious, what is the expected lifespan of such charging systems?
So the simple answer is no one knows what the lifespan of these systems will be, because they've not really been put out there and this hasn't really been tried. But you make a really good point, and that is we ought to at least try and time their lifespan to the lifespan of a pavement, right? So for example, we're talking about building systems, we're talking about putting them in as we rebuild the pavement, for example. So those pilot projects that we're looking at from an Aspire standpoint, we would do that rather than going into a pavement, say that we just rebuilt and retrofitting it. We would find a pavement that needs to be rebuilt. But we don't really know the lifespan of these systems yet. One of the electrical engineers said at a meeting one time when I asked him that question, he said he thinks the connections, the electrical connections will be the hardest, that will have the shortest lifespan, right? Because if you think about a pavement, it's moving around out there, whether it's, from the environment or from the traffic loads on it. So it moves, and that means these systems are moving around as well. And how's that going to affect the connections that have to be made? So that's one of the things electrical engineers are working on. How can we make sure this is durable enough to last? So, if I've got a pavement that is designed for a 50-year lifespan before I'm going to reconstruct it, how do I make sure this system's going to last that long as well? By the way, the system doesn't have to be in the entire pavement. So for example, I guess an easy, for example, for us would be I-74, right? Because it runs just south of us and goes towards Champaign, Urbana. We wouldn't necessarily build that whole section with this electrical equipment in it. There would only be certain spots along it where you would need that, right? So maybe you only have to have a 1 mile section every 20 miles or something to keep everything charged. That's something that's being worked on as well, trying to decide how often you need these.
And if I may, just a follow-up question, have your partners from the electrical engineering side tried to test to amplify the connection so then you can essentially go deeper?
Yeah, so they're working, again, I get lost in electrical engineering, right? I had one electrical engineering class as an undergrad, and I won't admit to how bad I did in that class as an undergrad. But anyway, they're working on those types of things, and all the work thus far, at least from what I get from them, tells them that they don't want that gap to get bigger than about 10 inches. But you're right. The problem is the bigger the gap gets, the more power you have to drive through the system. And for a heavy truck, we're driving so much power into the system anyway, that if we have to drive even more, it becomes really almost prohibitive to do that. I mean, think about, 200 kilowatts is quite a bit of power to have to drive into something like this.
Thank you.
Great. I think we have a small question again from Amir Malkuti in the chat box. He asked, has Tesla partnered with this project?
I'm sorry, has who partnered with it?
Tesla.
Oh, Tesla. No, I'm not sure that we've had any interaction with Tesla up to this point. But that's a good question, because you would think that they would be interested in it.
Again, if you have a question, you can raise your hand or you can put it in the chat box. I didn't see any question yet. So, Professor, I would like to ask regarding how this actually, the line is gonna be looks like in the road. So you mentioned that we just plug in a several segment for like 1 mile. So does it just gonna be like a dedicated line, especially for charging this EV? Is that what's going to be looks like in our road?
I think that's the thought right now amongst the transportation folks that are working on that, the adoption folks, is that it would be sort of like a you know, where you just a separate lane, just like you would have a high occupancy lane or something like that. It would be just a separate lane. And there would be, you would be warned that, that lane is coming up in, a mile or 2 miles, so that if you need to get into that lane to charge, you had time to move over and get into that lane and be ready to charge when you get there. You can see from a lot of the slides I have, at least, the pictures that we keep making show that it's green in color, right?
Mm-hmm.
I'm not sure why green, apparently because it makes people think of green energy or something. I don't know.
Yeah, I was just curious, especially for the heavy trucks, will we, and then the passenger cars, in the highway, will we join the same lane for the charging, or is it just going to be separate lane for them?
Well, that's a really good question. I'll voice my personal opinion. My personal opinion is I think as we rebuild at least the interstate system in the U.S., we should be rebuilding it with separate truck lanes. And I say that mostly from a safety standpoint, right? The other thing that kind of feeds into what the Aspire Center is doing is autonomous vehicles. And I don't know that I know a lot of people out there that want to drive their minivan around with their children in the back of it in the same lane as an autonomous truck, right? My personal opinion is we should build separate truck lanes that are separate from, our passenger vehicles. Now, whether or not that happens, I don't know. That aside, when it comes to this technology, if they're not separate lanes, then yeah, you'd have to use the same lane the trucks were using if you wanted to move over and charge your car.
Okay. But you mentioned that there was like the adoption team for this Aspire, right? Have you already started looking on the diversity of type of vehicles and EV in the interstate?
Yeah. So the adoption team has done some work. There was a project that was done that involved the Port of Long Beach, where they went in and did some work there about feasibility of putting something like this there coming out of the Port of Long Beach. There's been a couple of projects. There's one going on now that's basically a link from UPS is involved with it. It's basically a link from Seattle down to Portland. And so they're looking at some there. And those are the two that I'm most familiar with. There may be another project in Utah that they're also working on currently. But, part of it really is to try and get society input, people that, your average everyday people that are just out there using the road. What do they think of this? And how do we get them to, adopt this and think it's a good idea? That's part of it as well.
Okay, sure. So I think I don't have any further question in the chat box. So everyone, if you have questions, we still have a couple of minutes.
Thanks again, John. I think that was a really exciting presentation, and I think a lot of people are very excited about what's going on in this area. And some of our guys are searching also on this for electrification and energy harvesting. So that was really an important talk for them. So thank you so much for being with us, John.
Thanks for the invitation. I appreciate it.
Sure. I think we have a short input from Gary Herbert. He mentioned that one thing that I wonder about the rate of charging. Heavy trucks will use about 2 or 3 kilowatt per mile. Require very fast charging. Yeah. It's about the rate of charging for the heavy trucks. Okay.
Well, that's coming from Jerry.
Oh, it's just from Jerry. Yeah.
Yeah. Hi, Jerry. Well, so you're making a good point, but yes, it would be able to the intention is to be able to charge heavy trucks at highway speed, which for most heavy trucks is about 65 miles an hour. So it is fast charging, very, very fast charging.
Sure. Okay, I think it's about time we need to end this meeting. It's already 2 p.m. So thank you again, Professor Haddock, for this great presentation. I really enjoyed, and I believe all of us gained a lot of insight, especially how the electrification right now needs to be implemented in the future for our interstate, and especially for heavy truckers. So thank you again, and for this seminar.
Thank you.
Sure. And I hope we can see you again for all participants for the next Can Seminar series. Thank you all. Have a good talk.